Hello, welcome to our deep learning lecture. Today we will look at one common application of deep learning, namely computer vision. And we will start off by introducing a common technique to increase the dataset size that is available in computer vision. And that is image augmentation. In computer vision, we require very large datasets in order to train all the layers in a convolutional neural network or in an image transformer. These models, they have millions, billions of parameters, and they need to be trained in order to recognize the important features of the image. Often, we only have a limited amount of images available. And image augmentation is one technique to increase the number of available images. Not only can we increase the amount of images that are available, but we also increase the variety of the dataset. And as a result, our model will be made more robust to variations in the images. For example, say we only had a pristine training dataset, and in our testing dataset or in our application where we deploy our model, suddenly we sometimes observe blurry images. Then we would have a problem with a model that has been trained only on very high quality datasets. And image augmentation is also a way to make the models more robust towards these variations in images. So in image augmentation, we reduce the model's dependencies on some properties of the images in the training dataset and enable thereby the model to generalize better. So how do we do image augmentation? Well, one way is that we take the image and we crop it in random places. Other augmentations might be that we add blur to the image. We might modify the color distribution. We might shear the image a little bit. And by doing all these adjustments in a random manner to our training dataset and doing them multiple times to all the images in the training dataset, we essentially create a dataset that is much larger than the original dataset. So if we look, for example, at this image of a cat, one type of transformation that we could do is to flip the image either left or right. Now, if you think about flipping an image of a cat, well, it's very easy to see that the image still displays a cat. So for these types of images, flipping would be a useful transformation because it would not modify the class or the category of the object. Sometimes some modifications might not be ideal. For example, if we create a crop only to the background of the image, then the displayed category would not show the cat anymore. However, if we just flip the whole cat, it's still the whole cat. Similarly, if we flip the image up or down, the cat is a cat. Also, random crops are useful. So as long as we don't crop just a small part of the background, but rather crop into the image and still get parts of our cat, we will still be able to classify the content of the image as a cat. So also random crops are a useful type of transformation. While flipping left or right or up or down only has a single parameter, namely the frequency of applying these flips, here we actually have more than one parameter. Another type of augmentation technique might be to change the colors. For example, we can change the brightness. So if we parameterize brightness in relation to the original image, then we have a single continuous parameter for our augmentation. course, we can not only change the brightness, but also change the color distribution by changing the hue. For example, we might change the hue in a continuous range. And of course, we can combine changes in color with changes in brightness. Additionally, we can change the contrast or desaturation of the image. So in practice, we combine many of these augmentation techniques. So if you look at this overlay of multiple augmentation methods, you see that we started only with a single image of a cat. But just by augmentation, we have created a dataset of 8 very different images of a cat. Most of them for us humans would be very easy still to classify as a cat. And similarly, the neural network will learn to classify these images as a cat, but it will learn to be robust to these random augmentations. So the model will start to become invariant to these small modifications that we apply randomly to the image. So let's summarize. Image augmentation generates random images based on existing training data to cope with overfitting to the training dataset. So remember that one way to reduce overfitting is to increase the size of the training dataset. And while here we only have the dataset that we're given, we can use image augmentation to artificially create a larger image dataset using these random augmentations. For example, if we change color, brightness, hue, and so on, we would for each of those introduce a continuous range of parameters and then randomly sample the values and create our augmented images. Now the question is, should we apply augmentation only to the training dataset or also to our test dataset? Well, assuming that these random augmentations only make the problem harder, if we want to maximize performance on the test dataset, so in our real-world application, we probably wouldn't apply augmentation to the test dataset. And with this, I want to say thank you and goodbye. See you next time.